Hello and good day. This report is all about a particular variation of the electrical technique used in geophysical exploration methods, Mise-A-La-Masse. To have a brief recap, electrical geophysical surveys detect surface effects produced by electric current flow in the ground. Here, we will be discussing Mise-A-La-Masse. But before proceeding to any technicalities, here is a brief background of the technique. Mise-A-La-Masse is a variant of the equipotential method which was first introduced in 1912. It was one of the earliest electrical methods for subsurface exploration. Its variant Mise-A-La-Masse is still used today in mining ventures. The method was suggested by a French scientist named Carl Schlumberger in 1920. He described such as excitation of the mass. The method was originally developed to find subsurface ore bodies. Let's recall the difference between active and passive geophysical surveys. In active geophysical surveys, a signal is introduced to the Earth and its response is then measured. These signals may take on different forms such as displacement, electrical currents, or an active radiometric source. Passive geophysical surveys, on another note, make use of naturally occurring fields or properties of the Earth. Spatial variations are simply measured to infer something about the subsurface geology. Mise-A-La-Masse falls under the active geophysical survey. We will learn further upon discussion of its process. Mise-A-La-Masse is effective in the assessment of the extension and geometry of the ore body. Electrical energy is applied to 2 points on the ground surface. One electrode array uses the conductive mass under investigation as one of the current electrodes. Another is placed at infinity. The infinity electrode is an electrode placed at a distance that its electric field does not distort the electric field in the survey area. It is typically at a distance of 5 to 10 times the size of the mass being investigated. Current would flow because of the difference in potential. The potential distribution from these two current electrodes will reflect the geometry of the conductive mass, thus revealing the shape and extent of the body. All materials, including soil and rock, inhibit resistivity. Such governs the relation between the current density and the gradient of the electric potential. These variations reveal something about the composition, extent, and physical properties of the subsurface materials. Properties that affect the resistivity of a soil or rock include porosity, water content, composition, salinity of the pore water, and grain size distribution. Electric currents will follow the path of least resistance. Lower resistivity means it readily allows passage of the current. In this figure, we see on the right side the distortion of the equipotential lines due to the conductive ore body. If the medium between the two electrodes is homogeneous, the current and potential distribution is regular and may be calculated. When good or poor conductors are embedded in this homogeneous medium, a distortion of the electrical field occurs. Good conductors have a tendency to attract the current lines toward them, whereas poor conductors force current flow away. Here we can see setups that made use of the Mise-A-La-Masse method. A graph of the method schematic number 2 depicts the trend of the apparent resistivity. Mise-A-La-Masse can be performed in such setups shown. On the left, we see the body is an outcrop, that is, it is visible upon the surface. On the right, we see that the body is made contact with by means of a borehole and an electrode intersected with it.
The Mise-A-La-Masse method is developed to map the location of conductive materials in a homogeneous earth of lesser conductivity. Its unit of measurement is potential electrode coordinates.
Moving on to the main causes of the anomalies measured in the Mise-A-La-Masse method, it has been stated that most of the anomalies are found from the extension of the already located conductive ore bodies. So, as the main ore is detected, the next ore bodies that would be located are basically connected to the prior located ore body. Additionally, it has been proved through various studies that the shape and intensity of the anomalies measured in the Mise-A-La-Masse method are affected by numerous factors. To name a few, the anisotropy of the electrical conductivity, conductive layer, and topography affects the anomaly measured. Aston verified in his study through the calculations he made using the simple point source in a homogeneous anisotropic half-space that the anisotropy, or the magnitude of the electrical conductivity in the host rock, shifts the anomaly. As for the conductive layer, it was proved that the intensity of the anomaly reduces, as demonstrated by the model calculations in layered earth of both Poikkonen for the point source and Manifumbo for a conductive body. Lastly, the study conducted by Opliger exhibited how anomalies are clearly deformed through the topography or its physical and natural features. As for the minerals the Mise-A-La-Masse method detects, most of the minerals that can be detected directly are the conductive ores, given the main essence of the method, while the minerals it can indirectly measure are only the related minerals to the conductive ores that it can directly detect. The Mise-A-La-Masse method is normally used for detecting ore bodies with high electrical conductivities, given that the method uses a buried current electrode within the conductive body of interest. So naturally, it should really detect and it should be most suitable for conductors, which are electrically high conductive ores. Examples of the directly measured ore deposits are massive sulfide ore bodies such as pyrrhotite, graphite, pyrite, galena, magnetite, bornite, chalcocite, covellite, ilmenite, and molybdenite, which are metallic ore minerals. If the conductivity of the anomalous body is very high, there will be a relatively little potential drop across the body itself, and the buried body can be mapped at the surface of the Earth. With that, the potential patterns produced give information on the size, shape, attitude, and mutual relationships of the electrically high ore bodies, such as the galvanic contacts between them. This may then lead to the indirectly measured minerals such as zinc and tin. Overall, this method will help to the precision of the exploration and excavation.
Utilizing the Mise-A-La-Masse method of mining has its fair share of advantages and disadvantages to the people who use this in their mining techniques. One advantage of this method is that it allows for the effective mapping of the location of various ore bodies that have conductive properties, like copper sulfide, nickel, lead ore bodies, and other kinds of ore bodies that can be considered metallic in structure. The extent, dip, and strike of the ore bodies are determined with greater ease through this method. Another advantage of this method is that investigations of ore bodies near the outcrop or are otherwise shallow in depth can be performed rather quickly, since the equipment used in Mise-A-La-Masse are light, portable, and inexpensive. Said equipment consists of just transmitters, receivers, and the occasional borehole if the ore body to be investigated is in a deeper depth. Lastly, this method has a radius of approximately 3 meters in noiseless conditions, which can be considered a relatively large radius of action for the cartography or the mapping of a particular ore body's structure and geometry, as compared to the radius of other methods. With these advantages, however, come the disadvantages that arise when using the Mise-A-La-Masse method in mining. One disadvantage is that when the contrast and resistivity between the ore bodies and its surrounding homogeneous earth decreases, the potential mapping of the ore body's shape through this method becomes less precise. As a consequence, the mapped ore body geometry becomes less defined. When there is no contrast present whatsoever between the ore bodies and the surrounding earth, the precision of the cartography becomes distributed in more spread out hemispheres of potential. Another disadvantage of using the Mise-A-La-Masse method in mining is that the presence of other materials that are conductive near the ore body, like metal pipes, cables, fences, and electrical grounds, can make the interpretation of data obtained from this method a lot harder. This is because these materials can be picked up by the transmitter, and hence the data picked up by the transmitter from these materials can be confused for ore body data. Lastly, investigations of deeper areas require a lot of field time and longer conducting cables, since there can be times wherein no conductivity is detected from the shallower parts of the mine. Given this, the borehole used for the Mise-A-La-Masse method must be driven deeper into the ground to find more conductive materials, hence making the mining process a lot more time-consuming.